We are privileged with the presence of Dr. M.R. Anandaraman, alumni of Physics Department of Thoma College, now UGC BSR Professor Research, throughout the program. We welcome Sir to moderate this section.
Thank you. Thank you. So, shall we start?
Yeah, I'm okay.
Okay. Just a few, good morning, everybody. So we are into the second day of our Erudite series by Professor Raju Ramanujan, and a warm welcome to the second day to all the delegates. And yesterday we had listened to Professor Raju, especially on the cooling, magnetocaloric cooling. And today he is going to give a very recent advancement in manufacturing, and especially with the help of artificial intelligence and machine learning. This particular area is becoming very popular and very active, not only among engineers and metallurgists, among physicists and others. So I welcome Raju, Professor Raju Ramanujan, to give his second lecture on the Erudite series on additive manufacturing.
Thank you. Good morning, everybody. Thank you, Professor Anantaraman. Let me open my slides and then I will present. Okay, I hope you can see my slides. Is it visible?
Yeah.
Okay, thank you. Okay, so today's talk is actually different from yesterday's presentation. Yesterday, if you recall, I talked about magnetic cooling and energy harvesting, and focused on magnetic materials. So today also I will be talking about magnetic materials, but it will be an approach which is now picking up quite a bit of momentum. There are very papers in many high impact factor journals related to using artificial intelligence, using machine learning, using experimental tools also to accelerate the development of new materials. So this is the title, which is Accelerated Development of High Performance Magnetic Materials for Emerging Technologies, right? So I'm Professor Raju Ramanujan and from the Nanyang Technological University, Singapore. Okay, so let me go to the next slide. It's not moving. Just 1 minute. Okay, So now I will go through some of these topics. The last magnetic cooling I already covered yesterday. So this will be more on how we can do high throughput and use additive manufacturing. Professor Anantaraman said additive manufacturing is a good topic to be with which you should be familiar because it may be emerging technology for future. So we are focusing on magnetic materials, and in this talk I'll only talk about soft magnetic materials. And soft magnetic materials is a big market. It's used in electrical machinery. It's used in rotating motors, for example. It's used in transformers, distribution transformers like you have in the road, and but also small transformers, solid state transformers, then power electronics converters. It's also used in electric vehicles. It's used in wind turbines. And you can see from this graph that the growth in the market for magnetic materials is really increasing rapidly. Just to give you some feel, a huge amount of US electrical energy is consumed by motor drives. So just this 1% increase in the efficiency of magnetic materials, just 1%, can cause a big impact, positive impact on the total energy consumption in the world. So this is a topic which is of high industrial significance and significance in the context of green energy in terms of sustainability. But the field has to move forward in order to make superior magnetic components. So now we usually think of electrical motors. When you study in physics, you think of certain properties like permeability. You can think of saturation magnetization. So for soft magnetic materials, you want high saturation magnetization, low coercivity, high permeability. And because you want to reduce the eddy current losses, you want high electrical resistivity, right? So you want high efficiency, high power density. And now the motors for the next generation have to be working at higher speeds. They have to be faster. They have to be capable of working at high operating temperatures. So when you have high speeds, then you will have a lot of centrifugal stresses. So the mechanical properties become important. In the past, people will just talk about magnetic properties and separately from mechanical properties. But now we have to have a material which has good soft magnetic properties, high strength, which is a mechanical property, and high resistivity. So we need more than one property to be improved. In addition, if you want high operating temperatures, the Curie temperature should also be high. So now you have so many new challenges to be overcome. So just to give you some idea, you want to increase the resistivity, but typically the magnetization will come down. So this is a challenge. You try to increase the strength, but then the coercivity will go up, which you don't want. It's another challenge. You try to increase the frequency so that you can make faster motors. The loss increases. These show that we are facing a challenge. It's not an easy problem to solve. Also, in this case, you don't find systems which have high flux density, high and but low coercivity. That's what you want. So we need to now find a new way to a new set of soft magnetic. This existing, what is available today in the market, all has problems. So we need to develop further. Here, when you have a motor and it starts to rotate, there will be stresses, and that's the reason why then in the center. So ideally, you would like the high strength material to be on the outside. But as of today, there's no such material. Everybody is using uniform composition. To get graded compositions, you need to go for additive manufacturing. So this is one place where additive manufacturing can come up. So how to develop the new generation materials? So the traditional way of generating any new material, it's not only for magnetic, is very slow. Typically, it takes 20 years to develop a new material and put it into the application. We want to try to do it much faster. We want to, as I told you, there are so many challenges associated with getting this set of properties that we want. Soft, magnetic, high strength, high resistivity. So we would like to explore a big composition space and then use some AI techniques or some other techniques to analyze them. So in a typical process, industrial process, making graded materials is a challenge. But by using additive, we can make graded materials, compositionally graded materials. And here, as I said, we can use metal additive manufacturing. So in this part, we will discuss the combinatorial, that's the accelerated methods. You can combine this with various AI and machine learning packages. So I don't want to talk so much about the computer science part of it, but more of the physics and engineering. You can collect data which you require for the AI and ML programs by using many different techniques. Use additive manufacturing, you can use thin films, you can use other methods like diffusion multiples, so many different methods of making a wide composition space. So you can look at a variety of compositions quickly. In the old way, you'll just do one at a time. That will take decades to find out any promising composition. So just to repeat, the main aim is to quickly explore a vast composition space to find out which are the compositions that could have the best combination of properties. So here's the technique. This is additive manufacturing. It's a technique called LENS, laser engineered net shape. And the equipment looks like this. It's about the size of size of half a room or so. And here you have the powders feeder. The powder is fed into this machine, this equipment, at and deposits on this table. And you shine a laser, high energy laser, and that laser melts the powder. And then the powder mixes together when it melts and solidifies. So by using this technique, we can make this kind of metal alloy. And by changing the rates of the powder feed, for example, if you want more of this yellow element, you will increase the feed rate of the yellow element. If you want more of green, you will, so you, by using this different rates which you can control with. So one sample can contain many different compositions. So this is the beauty of additive manufacturing. In this context, we can explore rapid testing of the composition space, and we can develop compositionally graded magnetic materials. So I'd like to show you a video. And this laser is scanning the area. And the powder. So you're building up this material layer by layer. That's why it's called additive. So it's one layer after another. So you see, so this is the method for additive manufacturing. This company is Optomec. And by using this method, we can make such samples. Or we can make components also for industry. Okay, so there are many different processing parameters which we can change to change the quality of the how weight, layer spacing, flow rate, etc. And by using these techniques, we can produce different types of samples, different microstructures. Then we can use rapid property assessment. So we can use techniques in which we can do XRD of many samples, one after another, or even scan samples. So we can place a sample and the XRD will move from one place to another. We can use techniques like micro XRF for measuring composition quickly. We can use techniques like nano indentation, hardness, to measure, get a quick idea of the strength. So there are many different techniques we can use to do high throughput characterization and property evaluation. So this speeds up the process of assessment of our material. So now I'll come to some concrete cases. You know, iron nickel is a very well-known soft magnetic alloy. And we wanted to test whether we can make some iron nickel alloy which has good soft magnetic properties and good strength. So we deposited this material and then did the XRD. And we could change the crystal structure by changing the travel speed of the laser. And when you change the crystal structure, you can go from FCC to FCC plus BCC to BCC. And by this change in crystal structure, even for the same composition, you can get a change in the magnetic properties. So for example, you can see the magnetic properties, BH loop is changing depending upon the speed, travel speed. 5 inch per minute is different from 20 inch per minute because the crystal structures are different. So by using these methods, we can change the magnetic properties, we can change the saturation magnetization, we can change the coercivity. So we can tune the magnetic properties by means of using this additive manufacturing technique. Then we can extend this to ternary alloys, which people don't know what is the magnetic properties, because otherwise it takes too long to investigate. But here we can examine a range of molybdenum additions, range of vanadium additions. I just give one example here. You can add vanadium, you can add moly, and we can find the interesting low coercivity material by these additions. So we can get values of saturation magnetization comparable to the conventionally processed, but the coercivity is still higher than what we would like. So there is still need for further improvement. So how to further improve? We have to now look not at just one composition, which is what we did 30 nickel. We should change the composition. So we'll have X, FeXNi, and we will try FeX cobalt. So as I told you, we can change the compositions by using this additive manufacturing. So we can change from Fe22Ni all the way to Fe68Ni. And you can see as you change the composition, the crystal structure changes, which we find out from XRD. So we'll either get mixture of BCC plus FCC, that's here, or we'll get single phase FCC. And if you look at the properties which we can measure, we find that the materials which have good combination of MS and HC, which is this, but the hardness is still not what we want, because we want high hardness. The high hardness is here, but the high MS and low HC are here. So still we haven't solved the problem. So we have to keep doing more, but we can look at so many. You see, we can look at a wide range of spaces. Now we'll try Fe cobalt. So with Fe cobalt, we can change the composition. You can see we are looking at it in scanning electron microscopy. And we measure the magnetic properties, and we measure the coercivity. So you can see as we change the composition, the saturation magnetization keeps increasing, and the coercivity follows a complex behavior, but typically quite low at 70 ion cobalt, right? So by using this technique, we also measured the mechanical properties by means of heat treatment. So we did heat treated as deposited sample, and we did heat treated sample. And in the as deposited sample, the material which showed high MS and low coercivity did not show high hardness. But in the heat treated sample, we could find a material which showed high MS, high coercivity, a low coercivity, and high hardness. So this is, by using this method, we could identify a good new composition, which is not normally used, but by this accelerated development, we could identify material which has good MS, good low HC, and high hardness. So you see the power of this technique to accelerate the development of, to find out new materials. Now we can go further. We can look at ternary alloys, Fe, cobalt, nickel. So when you look at ternary alloys, we made so many different ones by this additive manufacturing technique. Otherwise, it will take so long to do by the conventional technique. But by this technique, we made so many samples, and we could check these samples, these ternary samples, right? XRD, again, we could change the crystal structure from BCC to BCC plus FCC. And now we need a ternary phase diagram to show these results. So we measured saturation magnetization, coercivity, and hardness. Hardness is a measure of strength. And you can see we want high saturation magnetization, want low coercivity, and high hardness. So beautifully, we could find a range of compositions by this method which show high MS, low HC, and low and high strength. You see, otherwise it would have taken, I don't know, decades to do this. So this is one of the ways in which you can use this method. So this is all experimental side. There's some more you can do. You can collect all this data. You can feed it into some artificial neural network program. You can use machine learning algorithms. You can combine this with literature values, what other people have reported, build up a new database and so on, right? So, but this, of course, experiments are always the truth. So this is good to have this information. And again, by using this method, we could find out some compositions that have good saturation magnetization and low coercivity and high hardness. So we found out that this is the composition, 7.4 cobalt, 11.3 nickel, which has both good magnetic properties and mechanical properties. So what have I shown you so far? I'm trying to show you that we can use new types of processing techniques. This is additive manufacturing I used, but we can do the same thing also by thin films. So you can make thin films and you can deposit in such a way that you get a wide variety of compositions and perform magnetic measurements and mechanical property measurements also. So there are other approaches which we are also exploring, but for today's talk, I will focus on the additive manufacturing aspects, right? So just to summarize, what I did was I want to improve beyond what is already very famous alloy, which is iron nickel permalloy. But how to do? I know that iron, nickel, cobalt, these are ferromagnetic materials, but how much of cobalt, how much of nickel, how much to add to iron, what do I have to do? And you see how we solve the problem by this technique in which we found out that by this composition will give us good magnetic and mechanical properties. So now we become more ambitious and we go for 5-component system. You see, to make a 5-component system otherwise would be very difficult. But by additive manufacturing, we can try to develop and find out new types of 5-component system. Another name for such type of 5-component system is high entropy alloys, because when you add more components, you increase the entropy. Now people ask, oh, you have 5 components, what will be the magnetic properties? Wow, 5 components, the composition space is vast, So we need techniques like additive manufacturing or other accelerated methods to assess the magnetic properties of high entropy alloys. So again, we use this technique, which I told you, the lens technique, to develop one sample has many different compositions. We change the compositions by changing the power feed, the rate at which the powders are fed into the machine, the lens machine. So it's quite straightforward. And then we'll get samples like this. So these are these rod-shaped samples. and we can measure, and we find, yes, we can change the composition. For example, change the chromium composition. We can change the uh, cobalt composition very nicely by using this technique. And now we have developed a 5-component system in which we are systematically changing the cobalt content and the chromium content. So one sample has many different compositions, and we find out what is the crystal structure of these particular samples using XRD. And we find out they have a BCC phase and then ordered BCC phase, which is called B2. We looked at it in SEM and we found, yes, indeed, it shows grains, these are grain boundaries, and equiaxed grains. And for some other compositions, for example, 0.8 and 0.6, you can see that there's a precipitation of a second phase. So now we can look at it in more detail using transmission electron microscopy. And we did this work and we could identify the features, structural features at the nanometric level using this transmission electron microscopy. So you can see some of our transmission electron microscopy results. And we can also measure the composition of the phases using transmission electron microscopy using the EDS, energy dispersive spectroscopy facility available in the TEM. So now we look at the magnetic properties. As I said, we are interested in those. And you can see, yes, as we change the composition, there's quite a big change in the magnetic properties. And if we plot the magnetic properties, as you increase the value of X, the MS is increasing, the coercivity follows a non-monotonic behavior. So in one sample, you could get about a variety of compositions. Then we could measure the Curie temperature. As I said, we want to have as high Curie temperature as possible so that we can operate at higher temperatures. So by using these type of techniques, we can use, we can accelerate the development of magnetic materials, and not only magnetic materials. You can use, this is why I gave this talk, you can use the same approach for making better dielectric materials, for example. For that, you may require some other processing technique, but you should see that there's a new approach available compared to the old approach. The old approach is too slow. So now we are able to, in a short period of lens, laser engineered net shape. Net shape is one of the advantage is that you can make it almost in the same shape as your final component. Your machining cost will be reduced. So one advantage of additive manufacturing is that you can make almost in the exact shape that you finally require. Whereas by conventional processing, you have to do so many steps in order to reach the final shape of the size of the component that you require. So we can use the lens process parameters, for example, the power, the speed, and many other parameters to control the crystal structure, to control the microstructure, for example, the grain size. Then here I showed you that we can take a combinatorial approach to the materials discovery. So this work that I am telling you about is part of a big program here in Singapore, and that has to do with the same topic, accelerated materials. And we are using a variety of experimental tools and also variety of AI and machine learning tools. Some other colleagues, not me, are looking, for example, at high throughput electronic structure calculations. How can you make DFT calculations and other calculations very quickly so that you can explore in theoretically what will be the properties of a wide range of composition spaces. So using this approach, we could find, for example, in iron cobalt, the right composition, which will give us the good combination of magnetic and mechanical properties. Similarly, for the iron cobalt nickel case, we could find a composition which shows optimum magnetic and mechanical properties. And for the ternary alloy, we could find out what are the values of saturation magnetization and Curie temperature when you add cobalt to this high entropy 5-component system. So we can say that this can be a promising technique, additive manufacturing, to develop magnetic components with value-added architecture. What we mean by value-added architecture, as I said, we can tune the size and shape because we are building it up layer by layer. So if you want something like this, we can make one layer and then keep on building it up so that we get the right geometry. There's another aspect, which is you can also bring in thermodynamics. So for example, if you want to, you find out that the FCC crystal structure has the best magnetic properties, you can do thermodynamic modeling using some programs like CalFAD to develop the phase stability. And by using this phase stability, we can predict which part of the composition space is likely to give us the right crystal structure. So there are a variety of tools we can bring into this accelerated methodology. Experiment is one part, thermodynamics is another part, first principles calculation is another part, then the programming using Python or some other package for analyzing this data, collecting the data from the literature to put into your database. All these are now coming up in a big way in future research in materials. So thank you very much.
Thank you very much, Professor Raju Ramanujan, for your inspiring lecture, especially on a very, very emerging topic on additive manufacturing, especially on tailoring magnetic materials for various applications, especially with the advent of EV vehicles and turbines. So this is a very niche area. So the session is open for questions. Maybe people please.
Sir, I'm Dr. John Berlin, Department of Physics. Shall I know about the XR? Sir, I'll already show a slide XR. Shall I know something more about XR?
So we actually in our project we just use XRF in the context of getting an idea of the composition. So you have to understand in accelerated method, right? You don't look at something in, it's a different technique. It's you look at correct composition, but you just want to get a rough idea because you want to know what is the space that is most promising. So for our project, we use XRF essentially as a technique for measuring the composition, but we don't focus on that aspect. Everything, right? So for example, to measure strength, in reality, we have to actually make tensile test and measure the strength. But then it won't be accelerated if we do for each sample. Tensile test takes a long time. So we measure hardness. So in the same way, we use XRF just as a technique for quickly measuring the composition spread.
Sir, I have one more question.
Yeah.
So you mentioned the value added architecture online. I want to something more about value added.
Your question is not audible properly. You take your mic and ask.
Sir, I have another question.
No, you take a mic because question is not audible to the audience, because the audience also need to know what is your question.
Am I audible, sir?
Now
Yeah,
it's clear. Okay.
Okay, sir. Sir, I have another. I want to know some more about value added architecture.
correct.
I want to.
Yeah. So what is this value added architecture? So if you look at a normal material, to make that material, you actually need, oh, there's some echo. Maybe now you switch off. Now you switch off the mic. What you do is you start from a big sheet, then you have to cut the sheet, you have to machine it. So there's a long process to go from the shape that you start with, which is huge, and finally to get the final component size, shape, and geometry. That's the conventional method. In additive manufacturing, you can build up layer by layer. So for example, you want a material which looks like a triangle. That's the component shape. And at the bottom, you want ellipse, but at the top, you want the circle. Because you're building up layer by layer, you can make the bottom layer small, make it elliptical cross section. Then as you build up to the next layer, you can make larger and build up to the circular. So in this way, it's called value added because what you get is close to the shape that you want.
Raju, before I forget, I just wanted to ask you a question because I tend to forget this. For example, you keep, means you started with your binary alloys and came to the ternary and then finally a 5-component system. So initially you were telling you are interested in modifying HC, you are interested in modifying MS, you are interested in modifying the mechanical strength, especially with respect to hardness and also the resistivity. To me, it looks like, for example, if you wanted to increase MS, especially you keep adding cobalt.
Yeah.
Am I audible, Raju?
And now you're okay, yes.
Yeah. You keep adding cobalt. At the same time, we also know from fundamental physics that grain size has a lot of influence on coercivity. And you also know that the mechanical strength is controlled by the Hall-Petch relationship. And even you can even invoke the grain boundary grain size in decreasing or increasing the resistivity. So to me, it looks like you increase cobalt. Maybe it's a wild guess. You increase the content of cobalt or whatever you wanted to. You increase MS, and you try to play with the grain size. Then you end up in the required HC or required hardness or required resistivity. So essentially, it means that this is a trade-off with respect to grain size. Am I correct or I don't know?
Yeah, so actually to simplify this presentation, I didn't mention some other parameters. So another parameter which is very important for engineering applications is cost. So the cost of cobalt is much higher than the cost of iron.
Yeah, almost 1:16.
So we don't actually, we want to minimize the amount of cobalt which we want to use for normal applications. It's not only cost, but it's also strategic material because it's only available from some few African countries which have some supply instabilities. So, so this is another factor. So it's if it was if it so this is another trade-off which I didn't mention because of the to make the talk simple. There are other aspects also. For example, oxidation resistance. So again, that will help us to put cobalt and nickel will help us from that point of view. So what we do actually, which I didn't again talk about, is that we use a programs called genetic optimization. And this genetic optimization can provide what is called fitness. So here you have all the trade-offs, you put it into what is called a fitness function. And this fitness function will develop a map or a surface called the Pareto plot. And using this Pareto plot, we can identify the trade-offs that are required. So, but to be to your specific point, right? The MS will definitely increase as you increase the cobalt, but as I have shown you, the HC varies with composition in a non-monotonic way, which we found out from this technique. Otherwise, we cannot easily guess. Almost the grain size is same, but because the composition changes, the crystal structure changes. The crystal structure changes, the coercivity changes. And this can give you a rough map as to where you're likely to get low HC over this whole composition range. So there are some complexities which we can find out by this technique, which are difficult to predict.
Because cobalt is supposed to increase the addition of cobalt because of its magnetocrystalline anisotropy. It's bound to increase the coercivity in any.
That's right. But there's also the crystal structure effect, which also affects. So rather we do the experiment and find out by this method. In case we can, if we are lucky, we may find out some compositions which have uh, unexpected, have good properties. So that's the goal, is to explore.
We'll discuss. I can always discuss with you later because audience has Sinoi has a question. Can you read it on the chat box?
Okay, so there are two questions. One is, can we control the particle size?
Before that, in ternary alloys, why TC is increasing with Fe? Can you provide an insight into the VSM measurements on graded samples? How signals are collected locally? Third question from Sinoi is HC and initial susceptibility for lens samples are more than the conventionally prepared alloys. Can you comment on this?
Correct. So in ternary alloys, TC increasing, no. Actually, for iron cobalt, as I'm not maybe I misspoke. I'm not sure, but anyway, the TC should increase with cobalt content. That's what I think we found. So that's the answer for the first question. In ternary alloys.
Yeah.
Okay, I'll have to go back and look at the data. I don't remember. For binary, I know what the answer is. Can you provide an insight into the VSM measurements of the graded samples? Okay, so we actually did VSM measurements by the standard technique. But now what we are doing is we are using MOC. We're trying to use MOC to quickly evaluate the magnetic properties without going to VSM. So we are trying to get a feel. You see, accelerated development is a trade-off. It's not as in-depth as conventional, rigorous physics type of methods. But at the same time, you gain certain advantages in terms of speed. So that's why it's accelerated. So instead of VSM, we are looking at how whether we can use other techniques to quickly measure the magnetic properties. So for example, I just give you a very simple example. We even use a permanent magnet attached to a force sensor. And we pass this permanent magnet with the force sensor over the sample. And by measuring the force of attraction, we get some idea of how magnetic the material is. So this is done in few seconds really. So that's how we are planning to do. But for the VSM itself, we are doing it in the traditional way. The third question is HC and initial susceptibility for N samples are more than conventionally prepared alloys. So that's true. The conventionally prepared alloys of magnetic materials are very, very carefully prepared. What they are done is they go through a lot of stress annealing. They go through a lot of grain size optimization. They go through a lot of compositional homogenization. They minimize the porosity. So in this lens technique, the one disadvantage is that because you're putting it through powders, there's possibility of pores formation. And these pores can increase your HC and reduce your susceptibility. So this is still unsolved problem. So if you want really, really best, it's still you have to go for the pore-free conventional methods. Those have been now saturated. Now there's no room for further improvement. So unless we do techniques like this to explore new compositions, then we can maybe even use those new compositions in the conventional way and try to improve these properties like HC. Okay, so that's the answer to the third question. Then there was another question before that, which is, can we control the particle size in this technique? The particle size of the powders is actually we purchase. There are people who make the powders. The powders are made by like the way you make milk powder. You take milk and you put it through a nozzle, and then you impinge that liquid with some gas, and it forms powders. That's how milk powder is made. These powders are also made by the same technique. So the powder size can be changed by the manufacturer of the powders by some kind of atomization techniques. But in our case, we just buy the powders. Now you may ask the same questions related to what Professor Anantaraman said about grain size. How does this powder size affect the final grain size? Yes, one can look into that. We haven't done that just because our goal is something else. Our goal is for down the road. But there are other people. There are other people who do research only on the process who do change the particle size. Okay, so that is that as far as the particle size is concerned. Let me see if I can find out the remaining questions.
Yeah. People can shoot questions in the chat box. There are a lot of time. Raju will be available for another 10 minutes.
Yeah.
Correct? Yeah.
Yes. So any other questions?
From Angel.
Here's one. Okay, I see one more. What is the role of the grain boundary effects of a material in controlling the magnetic properties? Yeah, so this is a good question. This is again related to grain size. And I think I showed you one transmission electron microscopy, TEM picture of those grain boundary phases, right? The reason we were interested in that is because typically the grain boundaries act as an obstacle for domain wall motion. So we want large grain size. The grain boundaries are not desirable for soft magnetic materials. However, the extent of control of the grain size by changing the laser power, by changing the travel velocity is not that much. If you really want to change the grain size, the way you have to do is what we did. I showed in one slide, which is to heat treat. So you anneal the lens material, and when you anneal the lens material, the heat treated material has a larger grain size, and that typically has a lower coercivity.
So, Raju, I have a couple of questions. I'm asking it for the benefit of students too. For example, because people are not very much aware of this particular technique, because when you shine the laser,
Mhm.
do you actually require a vacuum or?
Yeah, you don't require the vacuum, but the problem without the vacuum, what will happen is these are metal powders.
Yeah.
And if you don't use vacuum, you will find that they will get oxidized. But people in some other research, right, like Professor Narendra Dahotre, he does surface modification
Mm-hmm.
and he doesn't use vacuum. He does this like same thing which I'm talking about now, but on big components, like the size of your table or something like this. So that will not fit into such a chamber, right? So
Yeah.
what he does is he puts the metal and he does this laser. But what you can do then is to put what is called a shroud. So you blow some argon gas to
Okay.
form
Okay.
some kind of a blanket over it.
Yeah. Passivation, remove oxygen and things like
Yeah,
that.
it's not so fantastic, it's not so clean, but for engineering practical applications, it is still okay.
And one another small question is, because this is an observation from your one of your transparency, because in your binary alloy system which you have shown as prepared and the one prepared by the accelerated this thing, because I see that the, for example, you have shown the HC, because the uncertainty is quite very narrow in these two these things, because you have highlighted it and shown with respect to as prepared, and you have chosen the optimum composition. For example, it's something like say cohesivity is the difference is just one oyster or something.
It depends on the alloy system. I've only shown
No, I'm
you.
asking
Yeah.
the measurement uncertainty,
Oh,
plus or minus.
the measurement in this case, right? These are all done, as Sinoy asked, in the conventional way.
Convention.
This is
Okay.
just VSM.
Yeah.
Moving forward, right? We find that VSM is not really a very accelerated technique.
Mm-hmm.
We just wanted to get started, to get the research going. But going forward, we want to find faster methods of measuring the local magnetic properties. It's one of my PhD students is looking into that. MOC is one idea, but we are trying to see whether there are any other ideas. There are other systems like you can use big facilities, synchrotron and all those things. But then that defeats the purpose because you want
Yeah, yeah,
accelerated,
yeah, yeah.
and then you have to wait in for neutrons and synchrotrons. That's kind of defeats the purpose. So overall, right, in this field, there is some difference in philosophy. In this field, for this particular topic, you it is just like buying. I can say it is like buying fruits. If you go to a shop and you want to buy fruits, you will not say maybe thousands of apples. You cannot check each apple. It's not
Yeah,
practical.
yeah.
So you just take a look. You have some picture in your mind of what apple you want to buy, and you pick a few and come back home. Now, in this process is not a very rigorous process, right? This is the way, but in the way, it is much faster than checking each apple, right? So this is the same logic for accelerated development. In accelerated development, you do things quickly, but in this process, you don't do things as rigorously as you do in the conventional physics type of investigations.
I have another, because this is out of inquisitiveness I'm asking you. This is not related to the magnetic materials. For example, can you actually adopt this particular method? For example, your lens method. I don't know whether it is in vogue somewhere. For example, now we manufacture steel with this blast furnace and things like that. No? For example, can we actually extend this for manufacturing of steel? For example, you can control the.
There is a paper on nickel-based superalloys, on aluminum alloys, published in Nature, published in Science. It can definitely, I've not seen on steel, but it definitely can be done on steel.
Okay. No, that means in future, I think you see all these things in the
Yeah. There's a paper by Teresa Pollock. She's at University of California, Santa Barbara. I think she's published in Nature or Science on exactly conventional aluminum alloys, if I'm not mistaken. But people have published on nickel-based superalloys also. I'm sure it will be there on steel, but maybe I haven't checked it yet. But there are many advantages. I should say some disadvantage also. The additive manufacturing technique, compared to technique like conventional forging or casting, the output is less. So per hour, you will get less tons of material. So additive manufacturing cannot be used for everything. No,
Okay.
it's not at all
For specific purpose.
It's only for as value added architectures. It's only where you can add the value. For example, I give example if you want to make a metal biomedical application, hip implant. So right now, if you buy a hip implant, the doctor buys, there are only certain standard sizes. That standard sizes will not exactly fit any person. There will always be some, of course, because people are people. And so as of today, the hip implant that is put in your body will not exactly match your body profile. By using additive manufacturing and using the images that you can collect from the various imaging techniques like MRI, CT and all this, you can make the hip implant by additive manufacturing, which exactly will fit your profile. So this is how we actually improve our systems.
So maybe imaging also will help. For example, they take an image and then like this 3D printing.
Exactly. So what I'm trying to say is I don't want to oversell this additive manufacturing, but it can do certain things which others cannot do. Yeah.
We still have time for a couple of questions from students. I ask questions because students are very resistant to ask questions. Otherwise, I would have left it to students. Still, I expect. Where is Angel? Hello, Angel. Angel. Anybody have questions? Angel, you have motivated your students to ask questions. It's meant for them. It's meant for them. I invite students to ask questions because Sir is available for another 5 or 10 minutes. He doesn't mind even sitting for 5 minutes more.
Okay, sir.
Yeah.
I already asked them to ask questions.
But you have to motivate. You are the coordinator. Find out some ways to motivate them.
Okay, sir.
Say that you will give a cake or something like that. Audience, you still have time. Okay. I think we'll for example, if they are shy of asking questions, they can actually send their queries to Angel to people can
Okay, no problem.
via email.
Thank you.
It's a very interesting talk. I don't know. Shall I hand it over to Angel or sir or Marcus Matthew? Hello. Hello, Angel. Angel, shall I conclude or?
I already asked them, they had no questions.
Okay, okay. No, but you take the mic and speak. Angel, what I suggest is tomorrow you arrange a cordless mic for students to ask questions.
Okay, today that setup is not here, sir. Tomorrow onwards we can arrange that.
Yeah, you have to arrange, otherwise the professionalism goes off.
Okay, 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 sir.
So shall we conclude or wait for some more time for students to ask questions? You want somebody else to say thanks to sir or?
Yeah.
Yeah, please.
Thank you, sir. Now I invite Dr. Novelty at the Ham, Department of Physics, Thoma College, to the last report of thanks.
Thank you. Resource person of the day, Professor Raju Ramanujan, moderator, Professor M R Andraman, coordinator of the Erudite program, Dr. Angel Susan Cherian, HOD, Professor Santosh Jacob, participants from various parts of Kerala and even various parts of the world. A warm good morning to all. Today, on the day 2 of the Erudite series, we had a session on accelerated development of soft magnets. And we saw a specific technique called additive manufacturing technique Ramanujan. Let me take this opportunity to thank Professor Raju V Ramanujan for the valuable talk and the precious time.
Thank you.
So
let me also thank Professor M R Andraman, our alumni, for moderating the session.
Thank you very much. Thank you very much.
Thank you, sir. Let me take this opportunity to thank all the coordinators at the collaborating institutes for arranging special setups at their respective institutes to coordinate more participants at their host institutes. Thank you all. Let me take this opportunity to thank all the participants. We had almost 150 participants at one point of time. I hope there were more than 200, I think, joined in between. So let me thank all of them. And let's see tomorrow at the same time. We have an interactive session tomorrow at the same time. Hope we will see more interactions during that. Thank you all.
Yeah,
Thank you.
we are meeting at the
Bye-bye.
same time tomorrow again. Thank you very much.
Yes. Bye.
Okay.